Okay, so very good evening to all the participants of this course. We call it Fundamentals of Power Electronics. We'll try to keep a very wide range of this course, starting from something very basic and going all the way up to a very wide range, a very high range, so that it benefits the complete range of the audience that we have here. Please feel free to stop me and ask me questions wherever you like. So, I was giving you some brief background the other day in our informal session that we had. So, basically, if you want to summarize power electronics in the shortest way, we can just say that power electronics is nothing but a story of 4 types of power converters, which actually convert the AC form of power or the DC form of power to another form, or change the level of that, or change the frequency if it's an AC signal that you have, or it creates a variable frequency output from a DC source. So, any of these possibilities or options are there. So, here I will just very briefly summarize them for you, their operation. So, if I just take AC to DC converter with the basic topology, I can say that there is an AC source, and let us consider a single phase AC source, because we are just trying to understand the basic, reviewing the basic aspects of. So, let me just draw a bridge made up of rectifiers or the diodes. And these are the 2 points where the input AC supply. So, this is the input AC voltage. You can assume 50 hertz unless I state otherwise. So, these are the diodes which you can name as D1, D2 and D3, D4, and the output is coming here, and this is the load. I just show it as a box because I do not want to commit what kind of a load it is, but for simplicity of analysis you can assume that it is an R load till I state otherwise. So, let me just say this is the output voltage that is flowing, and this is the output current. Now, rectifier is actually a very common topic, and I am sure you have done in various levels of your education. So, you know that when you have a positive half cycle of this AC voltage, that time you will have this diode D1 and D4, they would be conducting. So, they will get forward biased. To basically get a diode into conduction, you must forward bias it. So, the AC voltage that we apply here, it has the tendency to naturally forward bias this D1 and D4 during the positive half and D2 and D3 during the negative half. So, when that happens, assuming a purely resistive load for simplicity, things will vary if there is a different type of load here. For example, it is very common to add inductive loads here, because when you will be feeding loads, you will have R as well as some sort of inductive load as well, component as well. So, but that we are not considering right now as a very first step or basic step. So, D1 and D4 conduct, and the current flows like this, and when D2 and D3 are forward biased by the input supply voltage, then D2 and D3 conduct in this way. So, if you have followed my hand as I have drawn this line, you can understand what is the direction of the current flow in this. So, basically what will happen is that now, assuming that these devices, these diodes are ideal and there is no drop across them, there is no voltage drop across them, I can say that my output would be something like this. So, these are basically the positive half of the AC cycle, the negative half of the AC cycle, again positive half. So, this is, they are alternating, but here on this side because the nature of the circuit is such that it is allowing the current only in this direction, unidirectional. So you get basically a DC output. This is your voltage, and if you take the average of this, and I just call it as V average, you can see that this is having a lot of ripple. So it's not, it's very common to put some filters here at this point. And the most common filter used is a capacitor. So what you do is you put a large capacitor here, let me call it CF, and if you want to reduce the size of CF, you can always use an L also, another filter. That will reduce the size of this capacitor because capacitor size depends on the ripple current that must flow through the capacitor, through this capacitor, or the ripple current which it must absorb. So by putting this, you will reduce this size. But the overall effect of this would be that now with this capacitor coming in, you will have this kind of a output voltage envelope that you will get. So basically it will remove these, whatever you see, these valleys and peaks here. All these things, they are removed. And more is this capacitor, this ripple will reduce, because now it will just, up to this only it will discharge, only up to this it will discharge, and like this. So basically this ripple will go on reducing. So you feel happy that, I am getting very nice DC output voltage. But as engineers, power electronics engineers, you must also try to see what is this current here. So let me just mark it as IAC. Now what you will see is that when this capacitor is put, a large capacitor is put, this voltage remains very close to the peak of this voltage. So this is the VAC, let's say peak. This capacitor remains charged to that. Okay. So now you will see that because the diodes will conduct, the conduction of the diode depends on what is the voltage between its anode and cathode. So you will find that on this side it is a voltage which is going like this, which is varying as per the natural tendency of the AC input voltage, but on the output side you have a DC which is standing almost at a constant value or maybe with a small dip. So you will find that these diodes, they will get forward biased for a very short time. They will get forward biased only for a small time, which is this time, and this is the only opportunity for the circuit to suck power from the AC side, absorb power from the AC side. So you can see that if this guy is demanding X watts, that entire X watts, the only possibility to absorb from the AC source is during this band, small band, because that is the time when the capacitor has discharged and the input voltage is taken over. You can see from here. So you can actually draw, because this is nothing but the lobe corresponding to the input AC voltage, you can see from there. So basically your current that will flow from the AC side, I am talking about IAC, that will be flowing only during this time, peaky current. And it will be also, because this is on the AC side, it will be the negative side, down. So I should be drawing it something like this, down. Then again it will be up, and then next time down, like that. This kind of a current will be drawn from the AC source. So why I am saying this, why I have actually highlighted this, it was not really necessary to immediately tell you about this point, but the rectifiers are infamous for the power factor problem at the AC source. Meaning that when you have these kinds of circuits working, you have these kinds of currents which are being drawn from the AC side. So you tell me, is it a good power quality? Is this a nice waveform that you really want your power network to bear or to face and to endure? No, obviously not, because if this is the thing, this kind of a thing is there, please understand that after all this your power where you have connected your load through this rectifier, there are many other consumers, other people who are connected on the same power network, and this current, mind you, is coming from somewhere, and it is affecting some other consumers also on the way, because there are voltage drops which will take place on the line, which will be very strange because of this kind of shape. So your voltage also distorts because of this, eventually what people get. So therefore there is a need for what is called power factor correction. Power factor correction, or simply called PFC, power factor correction, and it's very common in these kinds of power electronic systems. So I'll return to this PFC a little later, depending on the time, but let me just now take you to the next type of power converter, which is a DC to DC converter. Okay, so basically now the point is that suppose I have a primary source of energy that is a DC. Okay, now there are many ways a DC could be produced, DC supply could be produced. The most common is the battery that various types of batteries. You have other, of course you have the electrical generators that can, DC generators, they can produce DC electricity. And then you have some other types of renewable sources, for example. So talking about the DC to DC converter, we have primarily a DC source available to us, and we want from any of these sources, we want a DC voltage or a DC power supply depending on our application, which means that if this is at the primary source is at X volts, you want, let's say, at Y volts your output. Okay, so typically for these kinds of applications you have these DC to DC converters, and to give you an example which I probably should have written here, some of these very common today, from today's point of view particularly, are the solar PV, fuel cells, etc. In fact, even wind energy, I am not aware how many of you are familiar with wind energy and the wind energy conversion systems, but you must have seen many of these windmills as you go over the highways, that these windmills are standing, and when there is wind, a gush of wind, they are rotating, and because of the aerodynamic action you have a torque produced, and that torque is actually applied to a generator, okay, typically an induction generator. And this induction generator, now this wind turbine works as a prime mover, and the output of this generator is giving you electricity in the form of AC. But the problem is that because the wind speed is not controllable and it varies all the time, the output of that you will get from the AC generator, induction generator, would also be varying with respect to frequency particularly, and also of course the voltage level. So the best way of actually utilizing the wind energy is also by using the rectifier, the type which I just showed you before this. Only difference is that I have shown you a single phase rectifier, while actually for powers which are a little bit more than, let's say, 3 or 4, 3.5 kilowatt or 5 kilowatt, something typically that more than that, you need at least a 3-phase rectifier. So that part is not difficult because that is merely an extension of the single phase concept. So even in wind energy, renewable energy based on wind, I mean to say, you actually end up with a DC source. So now let me just tell you how a typical, just a representation first of DC to DC converter. So this is the, let's say, the DC source, I just mark it as VDC, and here there is a switch, and I do not want to tell you what this switch is exactly, whether it's any specific type of switch. It could be anything. Right now it is just an on-off switch for you, but it's an electronic switch which you assume that can be manipulated by us, and we can turn it on or off. Again, I show this load as a box, but for our simplification of analysis, you may assume that this is resistive. Okay, now as I was trying to construct the story and tell you, so basically let's say this is 100 volts and you want to get only 50 volts here. Okay, so we can just use this particular circuit as a typical conventional chopper circuit, and what I can do is that I can give an on-off signal to this particular electronic switch, which is something like this, and if I call this as a time period of this controlled pulse, continuous train of pulses, and I just denote it by t, then I say that there is some slice of this cycle which is d times t, or let me just say ts here. So d times ts, for which this device is on, and 1 minus during this time ts, for which this device is off. So when the signal is given, this device conducts and you have this 100 volts coming in here, and when you are in this particular region of the control pulse, then this device switches off. Okay, so what I am saying is that if I just denote again this by VO, I tend to denote the constant quantities by these uppercase letters, and those variable, time variable ones, like for example the AC, usually with lowercase letters. So that kind of a convention we can keep in the course. Many people, authors, they follow the same approach. So if I plot this voltage, if I plot here, how would it look like? It would look exactly like this. Assuming ideal switch, which means that it has no drops across it. I will say a little bit more about that a little later. So this is how your VO will look like, and because I want 100 to 50, I tell you that let's keep this particular thing as 0.5 into Ts, and this also 0.5 into Ts. If you do that, you will actually be able to get an average of this output voltage, which will be 50 volts. And of course, you can change this value of the voltage by playing with this number. So typically the control problem in all these such types of systems is that you play with the duty cycle, and electronically you implement a variable duty cycle to get the voltage that you want to have. Now this DC source I just showed as a 100 volts DC source. Now this could be a battery, it could be a generator, it could be any of these renewable energy sources. So irrespective of that, so we have kept it a pretty general and conventional system. So why this is called, in the beginning I said that this is called a chopper. Why is it called a chopper? Because you can see that it is chopping the DC, input DC voltage. If I plot, this is VDC, then you can see it is chopping it. It's called chopper. But the point is, with this kind of a system, this VO is always less than, or at the most it can be equal to VDC, in which case basically you are not doing any control. You could have directly applied this voltage to the load. There is no role for this particular converter. So now the question is that are there any variations that I can use which will also allow me to get a VO which is greater than or equal to VDC? Is it possible? So the answer is yes. And for that you must go deep into the into what is called a switch mode power supply. So in the beginning, conventional systems of this type, they were high power systems, mainly used as choppers. But later on, when the technology advanced, different types of electronic controllers came, magnetics became easily available, and also people could fabricate it more easily and so on. Then people, basically they ventured into switch mode power supply or switch mode power converters, those kinds of that particular field. So there you find that there are, apart from this, there are several variations of this. So for example, you might have heard that there is a boost type of a system, and this one particularly, this is called a buck type of a system, or there are systems which are buck and boost type of systems. And mind you, this is only basically a second order system that I have shown you. Second order I say because usually these kinds of valleys, these kinds of dips are not going to be liked by a load, particularly if the load is sophisticated. It will not appreciate that the voltage applied to it at such a high rate is actually touching zero at many points. It doesn't like that. There are some crude loads which for which this may be okay, but for sophisticated loads not allowed. So basically all I am saying is you need some sort of a filter here as well. And more is this frequency, smaller will be this gap, as you can see. It will shrink, and you can see that a smaller value of capacitor filter will be able to give you a nice output, DC voltage, constant, without any valleys, going deep pits, nothing like that, nice smooth waveform. And by adding some L and C kinds of components, not only that you can get a boosting of the voltage, as in a boost converter, you can actually have a combination. You can also have a buck as well as a boost system. Same system can give you both, and also you can actually reverse the polarity. Plus, you can also have some, not only the second order, you can have some higher order systems, typically fourth order converters, where you will find that these ripples, they can be further reduced. So you must have heard about some other converters like the Chuk converter, the Sepik converters, in case you have done that in your course before. So this is as far as the second type of basic power converter, the DC to DC, is concerned. Now there are two things I want to tell you here, because this I think is a good opportunity for me to explain. There are two things which I wanted to say here. One is, I want to tell you about losses in power converters. And please understand that later on we will be harping on this, we will actually get to this in more details for sure. Right now I want to tell you more as a layman, because I have not told you anything about the particular aspects of the power electronic system. We are just considering the very, very basic, the bare power electronic converter, the very basic component right now. This, plus I want to tell you something about what is called a switched mode operation versus switched mode operation versus linear mode of operation. Okay, now just the previous screen or the board where I have drawn that chopper circuit for you. Okay, now let's say that 100 volts DC that you had. Okay, this 100 volts DC that you had. Now let's say I put one bipolar junction transistor here as a switch, and this is the load. Forget about the ripple that will come in the output and so on. So this is 100 volts. Now there are two ways in which I can operate this switch. What are those two ways in which you can operate a bipolar junction transistor? There is a specific reason why I am telling you about I have taken the example of a bipolar junction transistor, because this is something that you must have read for sure, and also its operation as two basic operations. What are they? It can work as an amplifier and it can work as a switch. So what I am trying to say is that if you operate this as an amplifier, okay, it's like look at the characteristics, the transfer characteristics of a transistor. So I just say this is the voltage across the collector and the emitter, and this is the current that flows through the device. You know that it will be something like this. Now if it is working in this amplifier mode, it is here, and this works basically as a resistor. Now remember one point always, and when you are talking about power electronics with me or within yourself or with somebody else, there is no place for a resistor or a resistance in a power electronic circuit. If you are a good power electronics engineer, though I have not found such a good power electronics engineer yet, you will never use a resistor. You will never talk about a resistor in a power electronic circuit. It has no place. You should be able to manipulate your circuit, design your circuit in such a way that you will never use the resistor. The resistor should be present only in the load, where it comes to consumption of the electricity, where your power is going, rate of change of energy is going, that part. So therefore this particular thing, which this particular this particular scheme, this particular mode of operation, which is actually adopted by some of these linear regulators that you are aware of. Are you aware of linear regulators like 7815, 05 and so on? What are they? They are 3 terminal devices. On this side you give the input, on the output side you get whatever you want, 15 volts, 5 volts, but there are restrictions on the variation or how much could be the range of the input voltage. But understand that, let us say if you are giving 20 volts here and you are getting 15 volts here, please understand that this guy is dropping 5 volts. That balance 5-10 volts is coming here, plus it is supplying the load. So can you imagine the kind of loss that will take place here? If you take a very simple example, you will find that the efficiency of this system could be as low as some 40-50%, or in fact even lower. So I don't want to do this. What I want to do? I want to do switched mode. And switched mode is, now what is switched mode? Please understand, I'll just tell you, this is the, you can assume that this is an ideal switch definition, or the definition of an ideal switch, that when the switch is conducting, when the switch is on, the voltage across the switch is 0 or close to 0. Ideal case I am saying. And when the switch is off, the current is 0, the voltage could be something. Okay, so when I am using my switch in these two modes, you can see that whether it is on or off, the product of voltage and current across the switch is 0. But ideally that is the case, but practically that does not happen. Because if I give you this picture by drawing a diagram, so let us say if I just say that this is the current through a switch which is going up and down, and there is a voltage which is going like this. Now if it is going like this, very nice. Please try to see if you can make out, they're not very different the colors, but try to make out, one of them is voltage, the other is current. So, but that does not happen. If this happens at this transition, your V into I will be 0, but actually it is something like this. It goes like this and like this. They take some finite time to go up or down when you are switching the device. So there are 2 or 3 things which are involved now. One is that when the switch is conducting on or when it is not conducting, you can consider them as static conditions of the switch. But when it is transitioning from on to off and off to on, as here, that's another thing. You call it dynamic operation or the dynamic property of the device. So you will find that because of the non-idealities, neither this will be 0, this product of voltage and current during transition will be 0, nor any of these products will be 0. There will be some drop across the device. So this is what typically we call as the loss, and these are the main causes of the losses. So now you imagine that the previous linear control which I was mentioning, what kind of loss that will cause. If this is having also some small loss component, you assume, I mean you just imagine the kind of loss that previous linear regulator would have, very high. So the reason we prefer this, that even though there are some losses, but these are much less. So not only that you can try to get devices, something that we are going to read in this course a little later, we can also think of techniques that during the time of this transition, when a switch is going from off to on stage or on to off stage, you do something across the switch that its voltage or current, they become 0. You make at least one of them 0. You do some trick around them, and these are called basically the soft switching techniques of the power converters. So I think I have told you about the switch mode and the linear mode now. I have told you a little bit about losses. So this, as you know, would have a direct bearing on the efficiency or the loss of the power electronic converter that you are using. So both these things are. Now when you are doing your low power electronics in your class 12 maybe, or maybe first, second year of your bachelor's and so on, that time you never bothered about these losses, because you were dealing with devices which were all small signal devices. The variations of signals across them was not very high. That's all very small range, 5 volts, you would be dealing with some few milliamperes and so on. But one of the things that you have to understand here in power electronics is that now we are talking about at least a few kilowatts going all the way up to megawatts, and now even up to gigawatt of power range, very, very high. So efficiency becomes an important issue with these high power systems. It was not a very big issue when you people were doing your experiments in your junior classes. Okay, so we have done this, we have done this, we have seen the linear versus switched mode operation. Switched mode, I think you can understand, because we are using the switching device as a switch, not as an amplifier. We are using the BJT as I showed you, as a switch and not as an amplifier. Now let's come to a third category, the DC to AC type of power converter. Now assume again that you have a DC source. The primary source is DC. Assume. So that could be one particular case where you end up using a DC to AC system. If you need across your load a variable voltage, variable frequency supply. So that could be one option. But it's not very sacrosanct that you will always have a DC voltage and then only you will do that. The AC that you get from the wall socket, which is universally present everywhere around you, it may be an AC voltage, but it may be giving you 50 hertz, but that is fixed. You cannot change that. Now, if you remember what people told you about being able to change the speed of the induction motor, how you could change the speed of the induction motor? Do you remember? So one of them is that when you apply this voltage here, stator voltage, then one is that if I just denote it by this S, then I keep this voltage variable. But you know what are the disadvantages? That also you would have, those of you who have probably got some background, they would know that this is not the solution to change it. You can do it over a very small range, but other than that there will be a compromise with the torque produced by the motor. So the other option is what people told you, that you apply a Vs and F. You do not change Vs arbitrarily, you change Vs in such a way that its ratio with the frequency remain a constant. And they said, let's call it a V by F control, simple V by F control. Later on, of course, many other things happened, like field oriented control, vector control came in and so on and so on. I am not going into those details. Now this is a situation. This is a situation that you want a source which can give you a variable Vs, variable F, and this V by F is a constant. This is the situation, this is what you want. So that is where such systems, DC to AC systems, they are required. So the AC systems or the AC motors, as I probably told you during our informal session, that the AC motors came long back, but there was no way to achieve this because there were no control electronics and there was no switches available at that time. So people had to wait several years, 60, 70, 80 years to be able to efficiently control these AC motors. Now, having said all this, let me just give you a very basic inverter or the DC to AC converter. They are used interchangeably. So whenever you have a DC, it gives you an AC. Because people were at that time in the beginning more concerned about AC to DC, they considered DC to AC as an inverse process. So they started calling them as inverters, these systems. So typically you can see there are two legs, these two devices, these two switches, they are connected in series like this, and their midpoints, let's call them as A and B, and let's say this guy here is going to one of these stator windings. And likewise you will have an extension of this, you will have another leg, this and that leg, they will correspond to the second winding voltage, and then between this and that one with the third. So that will become a three-phase inverter. This one is a single-phase inverter, just for keeping for the ease of analysis and understanding. And because this is an AC output, inverter output, AC output, I have used a small v. I have been using this before. Now I am trying to use this. At least I am pretending to use. You can correct if I am not, somewhere if I am not put that way. Okay, so as you know that if I just call this a switch 1, switch 2, switch 3 and switch 4, and I say that S1 and S4 I operate together and S2 and S3 I operate together, which means that there is some control signal, there is some control I am actually exercising over these devices in such a way that I apply the control instruction to these two at the same time, these two at the same time, and let's say also for equal time. Let's say we do that. So how will this picture look like? I will say if I just say control pulse for S1, I denote it by G1, control pulse for S4, I denote by G4, and for this and this, I denote by G2 and G3. And I give them on and off control instructions, because that's all the only thing I can do. What else can I do with the switch? I can either turn it on or I can turn it off. And I just told you that almost all power electronics people are using switched mode. Either you switch this the device off, the switch off, or you turn it on. And for the remaining 50%, it is like this. So this total is Ts, and let's say 50% time G1, G4, another 50% time of Ts, G2, G3. So you can see that if I do that, what will happen is that when S1 and S4 are conducting, this voltage, if I call this again as VDC with a capital V, then what you will get is, if I can just draw it here, but not to scale, my VDC will appear here, then here it will be minus VDC, again it will be plus VDC, again minus VDC, and so on. So what is this waveform? What you see here, this what I have drawn, this is nothing but your VO. What can you comment on the nature of this VO? Is it DC form or is it an AC form of power? AC form. But it doesn't seem to be sinusoidal. Is it okay? Well, it doesn't really violate any fundamental principle, but there are other issues, like for example, it will have, as you know from the Fourier series expansion, if you have a square wave like this, it will have lots of harmonics. So if you are applying this kind of a waveform to this, a lot of harmonics are also going into the stator windings. Now if your machine is very expensive and it's very sophisticated, you cannot let that happen, because it will wear off the windings, insulation and so many things, will cause heating and other things, and it will flop the machine. The machine life will be reduced. You don't want this. So though you have obtained starting from a DC source and AC source, you try to make sure that this quality of this output voltage is better, not this, because you cannot apply this to your load. For crude load, okay, but for sophisticated loads, expensive loads, you will not like to do this, because this will be having lot of harmonics. It will be rich in harmonics. So it will have a fundamental component, sinusoidal, but it will be rich in the other components of the frequency as well, namely third, fifth and so on. Second will not be there as long as this waveform is symmetrical. So if I make it some 60% and 40%, then you will have some second component also come, because you will have a DC component in the output. And remember, I want to tell you one more thing here, that all these systems, whatever you see here, that they are all, people have tried with the advent of electronics and advanced controllers, they have tried things like the modulation of these pulse widths and later on sinusoidal modulation of these pulse widths, so that you actually end up getting at the output, these kinds of things. These kinds of components. If I just say these are the various components, there will be many of them. How they are generated, we will see later. But right now, I just want to tell you that people have tried. So basically what will happen, if you look at the spectrum of such an output, which you will get with, let's say, sinusoidal pulse width modulation, that these pulses that you are getting, you modulate them in sinusoidal manner, then the output would be something like this. And if you look at its Fourier transform, if you look at its spectrum, you will find that at low frequencies, this will be almost negligible. But at high frequency, so this is low frequency, or third, fifth, seventh, I am talking about that. High frequency, there would be some components corresponding to the frequency that you use to generate your sinusoidal pulse width modulation, something that I have not told you so far. The advantage of having this spectrum is that now, because most of the components of harmonics have shifted to high frequency, you can now put a filter here of a small size and you can try to get rid of that. So you can put filter here, small filter, low volume, low weight and so on, low size, small size and so on. So this is typically your system, which is a very basic representation and working of a DC to AC type of system. And I just told you a little bit also about the type of controls which are done. Now basically, as I was telling you some time back, these will be used very extensively in when you have AC loads, like for example AC motors, one of the major consumers of this kind of a application. Any questions? Please let me know if there are any questions. Can I repeat something? Okay, now how many of you have seen a fan regulator? Everyone has seen, isn't it? Just rotate it. Do you know what kind of a circuit would be working in a fan regulator? If I have to explain AC to AC type of power converter to you, I would say, see how a fan regulator works. Okay, now typically a fan regulator, or I should say conventionally, now of course even advancements have come, other types of devices are also used, but conventionally, very beginning, people were using just potentiometer system, a voltage divider system. And these are really like bulky regulators, and you would basically, they will be nicely attached to your switch boards and all that. And morning particularly, after a full night of the fan, when you will get in the morning, you can probably prepare your tea on that. You can put your pan on that regulator, and you can actually prepare your tea. It's quite hot actually, usually. Why? Because you are having a completely resistive network there, and you are dissipating power. So you were actually able to control the speed manually by changing that position of the voltage divider system or the slider, and you were able to decrease the speed or increase the speed at the expense of that energy that was lost there. So that was replaced by these AC to AC type of systems, and now even more advanced systems are coming. Now how they work, I'll just give you a very quick review of that. So now let's say we have a AC source, because I am talking about a fan regulator usually at homes. Let's say single phase AC which we get in our wall sockets, such is a situation. And now let's say I put a device which can conduct in this way or it can conduct in this way, and I connect my fan here, the fan terminals here on this. Now see the way these devices are connected. I am sure that people who still recall power electronics or who had power electronics as their major subject, for them it is not very difficult to visualize that I am talking about the switch silicon control rectifiers here. And this combination, in fact, such is the popularity of this kind of a circuit that people came up with a combination device which was called a triac, with only one control pin, because both of them are symmetrically controlled. So whatever pulses you are applied, control you are applying, it's at symmetrical points. So triac was a very popular, still popular device which is used here. So as you can see that when the AC voltage is positive, that time this particular device is in a position to conduct, provided you give a control signal to it. Okay, instructions given, please start. But if you do not synchronize it with the 0, so the moment this goes above 0 here, the input supply, if you do not give that pulse at the same time, then it will get delayed. So basically it will pick up after some time. So let's say you have delayed from that 0 point, you have delayed giving that pulse. So basically what will happen, you will, if you have given, let's say at this point, the output that will appear here will be something like this. Now symmetrically, now the second device also, if I delay its switching with respect to now this particular low, this is the low when S2 is now, as you can see the way it is connected, this is the one which will be forward biased or positive voltage across it, so that is in the position to conduct. So if you give, so here let's say if I just say I gave the turning on instruction here, to this I am giving symmetrically here. So this distance and this distance same. So what will happen now? There would be nothing here, but when the control instruction is given, then this will come like this, and likewise here. And as before, let me just call it a VO, small v, because I know it's an AC. You agree with me? This is an AC. This is what you get. Please remember, don't put this device here. You can't. This has to be here. That is the principle of this particular circuit. Don't do that. If you do that, the circuit won't work. I've seen many people making that mistake. Even in the case of rectifiers, I've seen people making that mistake. So you get an AC here, and whose amplitude, or sorry, I should say RMS, that will be better. So if I call this point to be alpha, this to be pi plus alpha, because this is pi and then 2 pi plus alpha and so on. And if I just control the value of this alpha, you agree with me that I will be able to shift it here or there, and I will be able to control the value of the RMS voltage that appears here, VO, across this load. So that is how it is done. Now the thing is, this is unlike the voltage or potential divider system, the original bulky regulators which will get very hot, because now you don't have any flow of power, you don't have a path for the thing to flow. So there is no loss, unlike the voltage divider system. So you must do one thing, just try to see the voltage divider system and say why I am saying it is lossy. Just try to verify that part. Okay, so these are some of the applications of the power electronics, having seen the basic converters, the four. They cover a very wide range of applications. So what you see on the top, on the left side, is basically a rooftop solar PV system. Lots of people are trying to use these solar PV systems now because there is a crisis of energy. We say that our conventional fuel, when it is generating power, for example, all these coal plants, okay, they are generating a lot of toxic gases into the atmosphere and causing pollution. People are concerned because not only it is affecting the people's health right now, but it is also affecting the ozone layer. So people think that the ozone layer, which protects us from the harmful rays from the from the cosmos, from the sun and so on, that is deteriorating because of these. So people are talking about sources such as solar photovoltaics. So this is a typical system that you see there. I do not know whether you can see the various, even I cannot see from here. Okay, but just to give you an idea, now solar PV source is nothing but it's a semiconductor PN junction. Okay, so if I have a PN junction, so we have a solar PV panel here, or a module, whatever you want to call it, and there is a light which is falling on it. And since it is made up of semiconductor PN junctions, basically what I am saying is that now the situation will be something like this, that you have this PN junction, you have this depletion layer, the center of the PN junction. So this is P, this is N, and there are photons which are massless positive charges, full of energy, not positive charges, massless energy packets which are falling. And now you have, as you know, lots of immobile ions this side. So any of these photons falling here in this region, because there are no excess electrons or holes which are already there as they are on this side. So these are all holes on this side, and these are all electrons. So when the photons are falling, some of these particles which are bound to the parent atoms, as in this region, they will get enough energy and they will cross over in the band gap energy diagram. They will cross over from the valence band to the conduction band, okay, and they will be free to move as current. Now when that happens, as you can see that let's say holes are generated, they will be pulled onto this side, and the electrons are generated because of this positive charge, they will be actually absorbed on the other side. So lots of holes will actually start accumulating on this side. So let me just, please assume that these are those excess holes plus which I have shown, original holes and the holes which are generated, which have come on this side, and here you have lots of negative electrons. Same way, as the photons will hit, they will be released and they will move on to this side because of this field. This field is positive and negative, so it will pull the basically your electrons onto this side. So basically what will happen, there will be a charge imbalance which will take place of positive and minus. So you will have a positive charge build up and a negative charge build up here. So basically what I am saying is that this will become a nice voltage source equivalent to a potential that is supported by this barrier, typically 0.6 volts, something like that. And now if you connect any load across it, let's say a bulb, then this bulb will glow if it is of appropriate voltage and current levels can provide. This is how a solar PV cell would work. The point here to note is that this is DC. What you get at the output of the PV terminals, module terminals, panel terminals, is all DC. And can I feed this into the load which is not DC? I can probably very seldomly I'll get some combination of PV cells that I'll be able to supply some DC load, but I will not be able to feed an AC load unless I convert this DC into AC. And you already know how to do that. You saw the third category of the power converters that we have seen where you can convert DC into AC. And the best way of using the power generated through this through solar PV, one of the very nice ways, efficient ways of using this power is that you feed it into the power grid and you make it available on the power grid. So it actually helps in so many other ways, but that is not really within the scope of this lecture, maybe some other time. So that's what you see here on the top, that you are actually having this grid, which is there is a meter along with the grid, and there is a power converter, DC to AC type. You can see, and there is also a battery, by the way. Battery is for because in the night there is no solar PV, you still want power, okay? Or when there is a power outage, you still need power. So for that there is a battery which will supply power. That's what it is trying to show, and then it goes to the grid through a meter. Now what that meter does, typically when you are drawing electricity from the grid, like what we do, it actually, we have to pay for it, right? But now here a different thing is happening. You are actually creating your own electricity using the solar PV source, maybe on your roof, and you are feeding it into the grid. So there is a meter that you need, a smart meter, which should be able to measure the power which is flowing from here to there or here to there. It should be able to do that. So these are smart meters which are required for this kind of a particular setup or this kind of an installation. Okay, then there are some other applications, and I don't want to really discuss them in details. You can see that there is a big power supply, lab power supply on the right side top, and this one here is a drone that you can see. And with all the discussions that we have had in our informal session on Friday and what I've been saying since the beginning of this lecture, I'm sure you have enough dose of power electronics. You understand that what could actually be going on as far as power electronic systems is concerned in a drone. Can somebody answer this question? What do you expect inside the drone? What power electronics you expect inside the drone? What kind of power converters, and do you expect some drive inside? Yes. You can see, because you can see a propeller there, there are wings, rotating wings and so on. So you can understand that there is power electronics. By the way, you arbitrarily choose anything around you, you will find power electronics inside. It's really amazing the way power electronics has touched each and every sphere of our lives. It's really amazing, okay? And then you can see one AC, air conditioning unit installed on the wall. So you can see, and can anyone guess why an AC has been shown here? Can you show one or tell me one example of a power electronics application that may be relevant to AC, air conditioning unit? Nobody. So do you think there is a compressor inside? Yes. Okay, so how does that compressor work? You need a motor, isn't it? So that motor, you control that motor. You need power electronics. And there are half a dozen other things which are there inside. That I don't want to really go into details, but what I am saying is whatever you touch, whatever you see is having power electronics inside. That was my idea of telling you with this particular slide. Okay, then I will leave this I would, from the pedagogic point of view, I would say there are various ways in which the power electronics has been basically defined by various people, and there are some definitions which I have given here. And they will be made available to you not only in the videos of this lecture, but also the reference videos that we will be sharing with you, all the information. So, all these big guys whose books you have been reading, they have given their own definitions of power electronics. But the simplest one is when you use to process power using electronics, or when you use electronics to process power, that is the best definition of power electronics as far as I am concerned. And then there are of course ramifications which actually try to highlight the other attributes of power electronics. So, I am not really saying that the other definitions are not useful, maybe for pedagogic and also reasons and also for your understanding, probably you should once go through these definitions as well, but for all practical purpose this is good enough. Now, power electronics is truly an interdisciplinary field. That is a very, very important thing, and that is one of the reasons why you find it everywhere around you. And people who really want to make things with their own hands, they want to create their own circuits, they want to control them, then power electronics is for you. Only thing is, you will not get to sit on a chair and work all the time. You will have to stand and work on a hardware setup. That is the difference. But these days there is a lot of software component inside power electronics, because people are using some other tools, software tools, which are also part of power electronics. But if you really enjoy making circuits and you feel happy when your circuit works and you are able to show that you have made some circuit or system work, then power electronics is for you. So, basically in general you can say control engineering, electronics engineering and power engineering, they combine in a way to form power electronics. So, power electronics is lying at the intersection of these three major fields. So, from pedagogic point of view you can of course see other things. Before I show you this diagram, I would like to show you another diagram, which is this. Okay, what you see here is now a very general diagram of a power electronic system, and where you see this green color power converter, basically it is one of those 4 converters which I just described to you, nothing else. I have just shown it with this green box, power converter. So, electrical output, DC or AC, or a changed frequency, changed amplitude, I do not know, but there is some electrical output which comes out, which is shown, and on the input side is a basic electrical input which could be DC or AC that we have discussed now. Okay, we have seen so many things now on that, right. So, that is fine. Then you can see that from the electrical output there is some feedback signal which is being fed into what is called a controller, and the output of this controller is generating that control signal, that pulse which I was telling you all the time. So, that is how it is going. So, can you see there are 2 things that you have to see now here. One is about the control of the electrical output, that is one thing I want to tell you about. The other is about the closed loop system that you see here. Both are related, but these are the 2 things. So, let us say that we talk about the AC to DC system, the AC to DC system that I described to you first when we started the lecture today. That was the first thing I described to you. Now, this AC to DC converter output is feeding some resistive load, let us say, and the voltage, as you can see from the 230 volts AC is coming through the diodes, it is appearing at the output, maybe you put some capacitors. So, you have a nice stable, rigid, stiff DC, you are getting a good DC. Now, but the point is, now let us say I change the load. Now, this resistance, let us say if it was 100 ohms, I have made it 500 ohms, or it was 100 ohms, I have made it 1 ohm. And it is required for my application that even though I change my load, the output voltage should remain same. Is there a way I can control this in that system where I showed you a diode, all the diode rectifiers? The answer is no, because it will give you a fixed voltage, and there is no way you can control, because when the loads will change, this voltage will change also, it will fluctuate, it will be losses, there might be internal losses in the system. Okay, there are so many other things in the system. So, it is therefore has to be understood that you cannot use just diode rectifiers, diode bridge rectifier for an application where you want a voltage regulation. Now, coming back to this diagram which is there on your screen right now, electrical output, if you assume to be the voltage output of your rectifier. Now you want to make it stable, you want to keep it constant. So you sense this voltage, you use some sensors, sensor technology, you use that voltage, you feed it back into a controller. Now this controller compares it with a reference signal and it tries to see how much you are off from the desired value. And based on that it generates an error signal and a control signal, and then it is automatically fed to a device which actually understands these control signals and which has a provision to accept these control signals. A diode doesn't have. A diode has only two terminals, input, output, anode, cathode, that's all. But if you remember your BJT, and probably if you have ever held a MOSFET in your hands, you would know that it has got three terminals, and there is one terminal which is specially meant for control signals. So basically what I am trying to get at is that if you want to control your output voltage, which is a phenomenon or which is a process called voltage regulation. So if you want to regulate, control your voltage, you must have a system in which your device, switching device, the switch which we have shown, it must be a three terminal device where the third terminal device must be able to take instructions of on and off from us. So a very big component of this course, particularly the first few lectures, would actually go in explaining to you the various switching devices which are there at our disposal. So there was a time people were using mercury arc rectifiers because there was no semiconductors. These mercury arc rectifiers or vapor rectifiers or whatever, there were several variations, they were not that reliable. Though they were able to handle very high power, they were not that reliable. Plus they were not able to do all these other four configurations that we have seen. They could not do those kinds of operations. So then semiconductors came, then as I told you, semiconductor diodes came, SCR came, BJTs came, IGBTs came, MOSFETs came, and the thirst and the hunger of the mankind, it doesn't subside with this. It says I want more. I want more in terms of I want to make my systems to be still smaller. I want my systems not to generate so much of heat. I want them to be cool. Okay? One of the ways to do that, fortunately or unfortunately, is to increase the operating speed of these switching devices. But the problem is, can these switching devices take those high speeds and still conduct a lot of power? So it so happened that the SCRs, which were invented the first, they could not operate at very high speed because they are bipolar devices and they have some issues. They could not, but they could handle a lot of power, but they could not operate at a high speed. On the other hand, some of the later devices like the MOSFETs and the IGBTs, they were not able to handle as much power as an SCR, particularly the MOSFETs, but they could operate at megahertz because they were not bipolar devices, they were majority carrier devices. You get my point? And now things are going even further down where people are talking about silicon carbide and gallium nitride as a semiconductor material. These compounds they are using now as semiconductors. They have now started going from purely silicon type of systems, and where very rarely people were using germanium as well. From here they are all going here. Why? Because these guys have the capability to operate at high speeds without causing lot of temperature increase or losses, and yet able to handle high power. So you will find that I will be devoting some certainly substantial time on this when we will come to it. But to understand some of these things, fortunately or unfortunately, we must revise some of the earlier, some of the more preparatory kind of material related to semiconductor physics. So that is my objective. I will be in the coming lectures, one of these days I will start with some of these semiconductor aspects, and probably will continue for a couple of or 2 or 3 lectures, and we will try to cover all these things. This is a general diagram showing any power electronic system in the world. That's what is the idea. There is nothing very big about it, but some basic understanding is required. Now, as I said, we have to prepare ourselves to take on the switches. Because we have seen by now the switches are the main workhorses as far as our power electronic systems are concerned. They are sitting at the heart, because in the previous diagram also you would have seen the power converter is sitting at the heart of the overall power electronic system, and power converter has a very prominent switch that you can see, and it is the switch which is doing everything. A very common I would say a very common question used to be, people say that if switches are going to create so many problems, they incur losses, they do this, they do that, why do you use switches? What is the problem? Why do we want to use the switches? So I am putting the same question to you. Let me see if you can answer this question. Why do we need switches? Because we want to control power. Because of that, I showed you that example of the also linear regulator versus that switch mode. You have to switch. How do you control? Your requirement is for the control, and that is what is making you use these switches and control them in a desirable way. That's why you get what you want to get at the output. That is why you need these switches. It's something similar to saying, asking somebody that can we have an electric motor without an air gap? So can we have a power electronic system without a switch, or without a switching of the switch? So it's just simply the same thing. Okay, now what you see, and this is the last slide about which I'm going to say today. I think that's the only time that I have with me today, and also you people. So you can see here a very important concept where I have discussed uncontrolled and controlled switch. I have just represented with a diagram. So now you, with whatever explanation I have given so far, whatever description I have provided to you of the various power electronic circuits, you guys know that the left uncontrolled switch is nothing but a diode. It has got two terminals. I mean, I am just talking about the ground or the reference point, not to be included in this. So one terminal with respect to a reference, another again with respect to. So everything is with respect to a reference. So diode, two terminal, as you can see, input and output, anode and cathode. There is no provision to control anything. So the moment you apply a forward bias across a diode, it will start conducting. There is no way to stop it. You get my point? So if somebody asks you, how do you control a diode? The answer is no. But then if I just cannot control it, why I am putting in my circuits? Why I am putting it in my systems? It's true that you cannot control it while the circuit is operating, specifically through, like you will do a 3-terminal device, by making sure that an appropriate voltage and current appears across the diode. You can ensure that the diode is either conducting or not conducting. So if your circuit operation you have ensured in such a way that a reverse bias voltage appears across the diode, when you don't want it to conduct, then it will not conduct. And so this question also is a very popular question which is asked by people many times. Okay. Now what you see on the right side though is the actual device. Now there are as you can see 3 terminals, A, B and C, and this we have written as a controlled or a controllable switch. Now typically there are 2 categories in this. One of them is the SCR, the silicon controlled rectifier. And I was telling you in the class that we had on Friday that an SCR is nothing but with a car whose brakes don't work. So you just start and you start driving it, and then the moment that happens, its brakes they fail. That's it. That is what an SCR is. So your SCR, the moment you apply a forward bias voltage across the SCR, it's a 4-layer device, by the way. And though many people have now, if you talk to people, they will not speak very enthusiastically about SCRs because they think they are old devices and they are so slow speed and so on. But please trust me, even today, some of the very high applications, power applications, are utilizing these SCRs. So SCRs are important. And the other thing I told you why we should still be studying about SCR, basically a 4-layer device, semiconductor device, why we should still be studying this is because we can understand power electronics with the help of SCRs. It really gives you that feel that what power electronics is doing if you are using SCRs. I will show you these circuits mostly with the help of these newer devices, but with the help of the newer devices, like as I said, MOSFETs, IGBTs and some of these new ones, I will show. But some of the videos to which I will refer you to, and which I would very strongly suggest that you go through, because that would be part of the course, is that you see how the SCRs work in those circuits. Those operations are there. So some of my old lectures I have been able to somehow get them back. I was able to access them. I had lost them for some time, and then now we can probably use them. So that is the point. So controlled switch basically is one of these modern day devices plus your SCR. SCR is a semi-controlled switch. You can turn it on, but you cannot turn it off at your will. But there are other devices which came off as an offshoot of SCR itself, like for example the gate turn off thyristors, GTU thyristors, where you could do a turn on and turn off of the thyristor. So those kinds of devices have been there and been used, as I told you, have been used extensively in some of the Japanese railway systems, to just name a few, just to name one such major applications. And the other devices, they are fully controlled devices, not semi-controlled, fully controlled, like your MOSFETs, IGBTs, power BJTs, and whatever devices which are there now. So we will be basically doing a lot of talk about this. Next time we will be just looking at the switching matrix, and we will look at some of the very inherent characteristics related to filters. We will try to understand physically what we mean by this. It all depends on how we view it as humans, right? Some people might view it as a matrix of switches. My power electronics converter, a matrix of switches. Some people might say, oh, now the current is coming, now it is not coming. So not coming means it must be infinite impedance. It's coming now, there must be some lower impedance, something like that. So they would probably see it as a network of impedances. So we will see both these approaches, and we will see, and we will try to appreciate this. One of them leads to what is called the switching theory of power converters. So very briefly I want to do that with you for the sake of completeness. And then we will move on to the greener pastures, the more modern things. Thank you very much.